welcome Armand V. Armand is a data scientist and manager with more than 15 years of experience in diverse industries. In this talk, Armand will present us the Playtika real-time recommendation engine and will share his lessons learned with us. Take it away, Armand.
Thank you very much. Can you hear the mic? Yes. Okay, perfect. So it's really a pleasure to be here in beautiful Lucerne to present you my team's work. Thank you for coming. Thanks to the organizer. Let me ask you a few questions. Yesterday in workshops, we discussed about models not reaching production. Someone suggested 80%. I think it's much more, but let me ask you the following question. Who wants to see his model in production? Come on. No one wants to see it in production? Okay. Who made it to production? Who faced production incidents? Who is afraid of production incidents? You should be and you should not be, because we learn a lot from that. So my talk is about a recommendation engine system which runs in production in real time. And I can tell you that it can be very stressful. It can be very stressful when we have production incidents with this type of systems, because we are not speaking about a batch system where the prediction failed to be inserted daily into a database. We are speaking about something which is happening in milliseconds and which can impact lots of users. So at Playtika, we build mobile games. We've got more than 34 million monthly active users, so that's quite a massive amount. And I want to share some lessons learned from prototyping to going to production with what we built here. So what is it we wanted to achieve? We have players, and each one of us, we have different preferences. Some might like challenges, some might prefer easier type of games, but also within the same game, we have meta games or different level of difficulties and content. And the big question is, what is the best for my personal experience? What do I like to play with? What is challenging me in a good way? So this is where we need to personalize recommendation, because we can really tailor what is the content to personal preferences. So this is about this system. This is an amazing team, which is really complete, from product owner to more architect to data engineers, software engineers, and machine learning scientists, also data scientists. So the business question behind is, how do we ensure that our games will provide fun experience to users? That's a big topic. That's a big question. And we've built this platform which reacts upon real-time events. So an event can be, I just log to the game, or I level up, or I'm about to start a specific meta game, or anything else. And this will send a message, Kafka message, to a platform that will be making a decision of what content to give you. It can be a quest, it can be pop-up, welcome back, it can be anything. So it's about experience. And from this experience, as a player, I will like it or I will not like it. And this feedback is super useful for the platform to know if it should continue to do it more or less to similar people like me. So it's all about online models, in particular Bayesian models. And Bayesian is very elegant because it's a class of statistics where we can make inferences with limited amount of data, meaning we can learn super fast, and we can react dynamically to changes in the game. For example, there is a new game content which is changing the way people are experiencing it. We want to adapt. Or there is a new type of experience, like a quest, we want to adapt. So in this context, we cannot use classical recommendation system like collaborative filters, because it assumes that you know what is going to be the impact of whatever you're going to recommend to your users. Here, the beauty of this system is that you can start cold, meaning you have no clue of what's going to happen, and you can refine over time. So you can give things randomly and evolve into a situation where you know this is good and this is not good. So it's all about this feedback, positive and negative, which is a user-level feedback. Okay, so what's a bandit? It's all about probability distribution. I think that this recommendation is going to be good at, let's say, 60%. But what is the uncertainty around this 60%? I can simply model it with this, which is a beta distribution. And when we start, it's a bottom one. We don't see the laser, but it's an untrained model. So we can say we have a flat prior, which is a uniform distribution. So it might be good, it might not be good, I just don't know. So I'm going to sample at random and say, okay, this specific action might be good at 25%. I will do a similar draw for another type of recommendation, and maybe it's 70%. So I'm going to use this one. And with the feedback, this random distribution is going to evolve in shape towards one of these three types of distribution. So the good one on the top, we know it's good at 80% of the cases, and because it's very narrow, we are very confident it's good. So that's a very useful learning. The bad distribution is also a very useful learning because we know that it's good only in 20% of the cases, so it's not a good recommendation to make. And also because this distribution is very narrow, we are confident it's not a good action to propose. The ugly is really uncertain. So maybe we didn't collect yet enough feedback to learn, or maybe we need to stratify better the users in this space. So let me give you a real example of treatments of what we wanted to propose as content to former churners, so people who had left the game and came back. And this is a very difficult use case, because you don't know how the player is going to react, and you have one chance to make sure that he's enjoying the game. So in this movie, we started from a flat prior, and with the feedback, it evolved in only 23 iterations of feedbacks. And what's beautiful is that from a cold start example, we learned what was the optimum situation with less than 7,000 users. It's a very small amount of users. So a good game at Playtika is about 1 million active users per day. So you can see that with this system, we can learn very quickly, very efficiently, which allow us to not test one or two actions, but much more. So we can really test a lot of things, a lot of combination of experience. Now that's the infra which is behind. So we've got the game, they send triggers in the form of Kafka messages, and it goes to a specialized infra, which is really a streaming system, real-time system, whereby the model will make an inference and send it back to the game. And the feedback can be computed instantaneously or with a delay, depends what is it we want to maximize. But it will go to this feedback infra component, which is also very elegant. So it's a batch system. We don't need to do it real time. We could if we want, but we don't. We just aggregate feedback daily, and we refine the model. And with this, we automatically redeploy the new version of the model. Now, what's behind is it's really following the best standards in terms of distributed systems. So it's all about decoupled microservices approach. Why? Because it's more scalable, it's easier to maintain, and with the same exact piece of code but a slightly different configuration, you can get two components for the price of one that will do two specialized functions. So you can build a pipeline which can be simple, but which can also be fine-tuned to more complex infra with exactly the same piece of code. So it's very elegant. On top of it, you can deploy with Kubernetes, and you can really auto-scale. You can up or down scale according to your demand. So you can have high availability, high throughput systems. When we did the stress test of the systems, we can cope with thousands of events per second. So this scalability is super important in production. Attached to it, you can really monitor every single component. You want to make sure that they are fully working as you expect, and if they don't, you just want to raise alerts and to intervene, or you want to automatically restart the component. Again, this is possible with Kubernetes capabilities. And all of that can be part of a much more complex ecosystem of infrastructure. So it's really a separation of concern. What are the lessons learned? So I'm going to present you a few lessons. It's not exhaustive, but I wanted to make a selection at the product level and at the technical level, and also some insights at the data science. So let's start with the business question. So you see the big question was large, but it needs to be sliced into something which is much more simpler to address and to start with. And it's all about defining what's the value, what is it we want to do, what is going to be the impact, and how we can assess this impact so that we can really assess the feasibility and we can assess the risk. And feasibility can be business feasibility, but also technical feasibility. If you want a real-time system with a deep neural net which has a latency of less than 1 millisecond, it's going to be very difficult. What are the risks? You need to consider what could be the impact of a faulty system running in production so that you can minimize in advance. So all of that is really the basis of project management, but it's super important for a successful project. Now, the team itself needs to be fully autonomous, needs to have all people which are required to make this project move. So it's Scrum. We are not reinventing a new framework. You see the type of people that we've got part of the team, but again, multidisciplinary and self-organized, and no manager. So this is kind of a joke, but it's true. You don't want your leaders to intervene into whatever the technical people are trying to build, because you will lose more time to explain and to convince. Just let the team run, make the decisions they believe are the best, show the increment, and refine according to the feedback. And this is a way to go super fast in terms of prototyping. It's also a way to learn and to anticipate what will be the next value that the product could bring. Okay, now let's talk about the architectural design. That's really fundamental. You don't know exactly how your product is going to look at the end, but you really need to invest time to think what is it you want to build. So start with something very simple. Don't go with a distributed monolith. You don't want to go this way. Start with something where you can plug different modules, because it's much easier to maintain. And if at some point one component starts to be big, you can give it to a dedicated team. You can also get this modularity, which will help you to build more and more complex systems. And you want components to be versatile. So don't hard code what you need to do. Use configuration-based systems. Linked to it, don't reinvent the wheel. There is a lot of open source elsewhere, very good projects that you can learn, and I'm just highlighting AkaStreams, which was proposed directly by the developer. It was an addition to the tech stack, and it was a very good decision. Why? Because this is a very efficient system for streaming. It comes with a lot of advantages. I'm listing just 4 of them, so responsive, resilient, elastic, and message-driven. I'm not going into the detail. I just want to say that it's a framework which allows the modularity and the performance of what we built, along with the security, because with the actor supervisor schema, any faulty component can be restarted automatically by its supervisor. So it's not only very elegant, but it's also very efficient. Now, the performance is extremely important in this type of systems. So it's definitely worthwhile to invest into stress tests. This is a quick example of throughput, so it's a smallish type of example, but still it demonstrates the type of events, the throughput that we get into use cases. So 75 in this example, with an infra latency below 7 milliseconds, so super fast. Now, that's on the infra. What about the model itself? So what we did was to build a Python implementation of Bayesian bandits, which we open source, and we welcome contribution. It's unit tested, it's documented, and it's completely use case agnostic. You can use it for anything. You can even use it for offline analysis, and we do provide a lot of offline policy evaluation capabilities. And it's fast. And this was a very big requirement, because the initial implementation that we've made was 30 seconds to make an inference on one specific experience. Let's say you have 50 experience, and you need to react in less than 20 milliseconds. It's impossible. With the re-implementation and some optimization, very good work from machine learning engineers, now it's few milliseconds to make an inference. Real-time monitoring and alerting. It's critical. It's really critical. So expect what could be the worst and prepare alerts for it. And even if you're overly pessimistic, it's good, because you can say, okay, maybe this was a false alarm, I don't want to use it anymore, but at least you know that you are covered. And it goes together with adequate testing as well. It's needless to say, but still. So, and it's not only about unit testing, it's really integration testing and make sure that the system will react in the best way. But in scenarios where you cannot fully assess end-to-end system because it can be challenging or you don't know if it's representative of the real life, real-time monitoring will save you. Also, you want to define from the start a clear SLA so that you know exactly what needs to be done if an alert is triggered. And one thing which is a relief to everyone is to give a kill button to your stakeholders. Even better is to give an auto-kill button, which will kill himself the infra upon some critical alerts. One point, which is not a joke, is be woken up at night. Why? Because if you know that you are getting to be woken at 4 a.m., you will spend much more time to avoid this situation. And when it happens, and it did happen, you will make sure that it will not happen again. And also, you get much more example of what was missing in your code base or in your system, or maybe a slightly different situation, which you also want to cover. So in our case, we got woken up with really edge cases, and we got woken up because of other defects, like the Kubernetes cluster being down, or some Kafka lag. So really minor things. But still, it's a very useful thing to do. About the alerts, improve all the time. Add more, remove what's useless, so change as necessary, change the threshold because maybe it's too stringent or not stringent, so it's a dynamic system. And it goes with what I said, being woken up at night. It will give you a feeling what is a good threshold to apply to your system. So these were the few kind of lessons that I wanted to share. So just to recap this presentation, it was about real-time recommendation to millions of users. And we both monitor the performance in terms of infra, in terms of ML very closely, but also the business impact, because we don't want to provide bad experience to users. It's not what we want to do. And the launch of any new use case is also subject to very controlled A/B test frameworks. So it's not only useful for the business, but it's also mandatory for whatever you are going to put in production. Don't start full scale with all possible users of your segments. You don't want to do it. Think canary type of deployment. Start small, internal users, increase maybe 100, 1,000 users per day, see how your system is reacting, and then slowly you increase the population. And when you are fully confident that you master everything, then you can roll out to all of your user volume. With that, thank you very much. I'm very happy to take your questions.
Hi, thanks for your presentation. What kind of content do you recommend? I'm assuming they're free-to-play games, so there must be some sort of in-game shop.
Exactly. So the content is more in the type of quest, like which type of quest is better for you to complete. And within the same game, you can play different way because you have the main content, but also you have meta games around. So if the quest is you need to play this specific map, or you need to complete this puzzle, or something else, that's a quest. But you and I, we have different preferences. Maybe you don't like puzzle, I love puzzle, or vice versa. So it's always very difficult to know in advance what is preferred by the player. It can also apply to the type of challenge. So do I want to put a very difficult challenge or a much easier challenge? And when it's about playing cards with other people, who are you playing with? If you play with super experienced player, you will lose all the time, or most of the time, so it's not nice for you. You want to kind of balance this type of situation. And conversely, if you are very experienced, you don't want to play with newcomers because it's not fulfilling. So it's very delicate to manage this ecosystem. What you can do to one user can impact the rest, so it's also things which we take into consideration.
Thanks.
Thanks for the talk. I'm curious, how did you classify the users? Because, I mean, to make a recommendation, to learn what's your type, you need to come up with classes or types of users. How did you approach that?
Yes, so very good question. There are not two definitions, but two angles. One is coming directly from the business. Let's say you know that you have lost some users and you want to prevent similar users to churn. So you have, let's say you have a prediction model which flag every single day who is likely to churn because his interest is decreasing. So that's one segment which you want to tackle. So that's onto the business aspect of what is a use case definition and what could be a palette of good treatments or good experience to provide for these users. That's one aspect. Second aspect is more data science. So we have two types of algorithm here. One is called stochastic multi-arm bandit, which doesn't use any data. So because it doesn't use any data, there is no stratification. But you can pre-stratify ahead with a classical segmentation approach to make sure that in your business segment, you have sub-segments of players which are more similar in terms of characteristics. That's one angle. Second angle is much more sophisticated. It's using contextual multi-arm bandit. So contextual multi-arm bandit needs a context, meaning characteristics or features on a player. And the system will itself try to find what are the good weights according to user characteristics to make a good recommendation. So it's kind of doing a mini segmentation inside the recommender. It's a little bit more sophisticated than that, but it boils down to it. And that's one way to make sure that this specific experience is sent to people who will like it versus something else which is better for other type of users.
And for the latter now, you would impose certain features first. You would say, okay, like this guy spends that much money, or kind of the money spent in the stores, the time played.
Yeah, it can be anything. It can even be the type of device, if you play on your phone or via Facebook or something else. So, you might have some very good clue of what is going to be useful. So you can say, okay, this is my default list of features. But also you might say, I don't know. So what if I were to add this, and this? And then with the system, with L1 and L2 penalties, it will find itself what was useful and what is not useful.
Thanks a lot.
Sure.
One more question.
Just a quick question. In your talk, you said collaborative filtering is, in your use case, not possible. What's the reason behind this?
So the reason is because of the need of data. You need to know, you need to have data on your players, and for some of them, you need to know what is going to be their response when they get exposed to an action. And most of the time, you don't know this in advance. Why? Because it can be a new content that we want to release to the game. So you have no prior knowledge of what it's going to be. And this is why Bayesian comes to play, because you can have a belief. I think it's going to be good at this amount, but I'm not sure. And I will let the system fine-tune.
Thank you.
Okay, last question, and then unfortunately we don't have a break for the next one.
Thanks for presenting the nice work and also for your relatively fun and colorful slides. So that's what we expect from a gaming company, right? So my question is about your data and your machine learning model. So do you actually, I wonder, if you consider each individual user as, and also the game that you have as individual nodes, or do you also consider the edge connection between the user or the game? So is it kind of graph?
It's not a graph-based model. And these systems so far are applied onto a game level. So they are not applied across all possible games because the variety of game is so different that it's very difficult to model what is going to be the player behavior. And also the type of experience is very different. So from a puzzle to a game card, it's very different.
Okay, thanks.
Thank you. Thank you very much.
Thank you very much for the question. Thank you, Armand, for coming.
Oh.
Please rate the speaker in the app.